Hi folks, thanks for having a little patience. My name is Rafael Cos, and I'm one of the organizers for the Future of Data Meetup Silicon Valley. So tonight we have our talks around getting started with Apache Spark, Apache Hive on AWS, right? And we have a couple Apache committers, Alan Gates, Miliang Liu, and Gopal Vijay Raghavan. So without further ado, we'll get started. We'll get Alan going. So we are actually live streaming it, and the replay will be available. So with that, we'll get started with Alan.
Thanks. All right, cool. All right, so for those on the live stream, I'm Alan Gates, and we're going to talk today about Hortonworks Cloud and AWS. So I wanted to give you just a little introduction to what's in there, and then show you kind of a brief demo of what it looks like to look at the get a cluster started and run it online, or run it in the cloud. So what is this? It is an offering of Hortonworks distribution in AWS Marketplace. And right now we're focused around offerings of Hive and Spark. So those are what's there today, and I'll show you a little bit more of that in depth in a minute. The focus here is really around quick ephemeral clusters, not necessarily long-running ones, not a little different than in on-premise where you're going to put something there, spend a long time installing it, tuning it, getting everything just right, and then run it forever. Instead, this is focused around, okay, I can set up a cluster in 15, 30 minutes, run my day's worth of jobs, shut it down, done, gone. Right? So very, very agile, very quick, and definitely ephemeral. It's pay-as-you-go pricing, and there's options for either hourly or annual rates on that. And the optional free community support. So I'll talk a little bit more about that later, but there are some support options available. So what kind of clusters can you spin up? Right now we have 4 different pre-built clusters that you can spin up, and pre-built in terms of what's installed, not in terms of size. You obviously get to pick the sizing as you set it up. So the first one is focused around data science with Spark and Zeppelin. And this one is, the green check mark here means that this one is considered stable. It's GA quality code. We feel safe telling our customers to run this in production on their important workload, their critical workloads. The next one is data warehousing / ETL focused. That comes with Hive 1.2.1 and Spark 1.6. So running HTTP 2.5, again, this is production quality. We expect people to be doing both ETL type work here with Spark as well as queries with Hive or Spark SQL. And now the next 2 are a little bit more for the brave, a little more out there in front, kind of what we would call tech preview, which is why you see the little yellow warning sign there. So this is a newer iteration of the EDW ETL, one with still with Hive 1.2, but with Spark 2.0, which we have not yet released as GA. So we're still shipping that as technical preview. And then finally, an analytics cluster with Hive 2 with LLAP. This is our new set of daemons inside Hive that make sub-second queries possible. Gopal will be talking a little bit more about that in a bit. But this one allows us to really do interactive queries, and it includes Zeppelin, the notebook, so that you can do those queries very easily. So how does this work? There's actually 2 products in the marketplace that you use here to put this together. One is the Cloud Controller, which is where you actually go to start up your clusters, tear them down, that kind of stuff, and I will show you this in a bit. And then there's the clusters themselves, which are a separate product in the marketplace. So you actually need to subscribe to both of these products. And So you would go here, you start a cluster, and you can run, of course, multiple clusters at a time, and you can connect to each of those and run them. And again, I'll show all this in a bit once I've given the overview. Inside a cluster, we divide the nodes into two types just to keep it simple, master nodes and worker nodes. Master nodes are things that are going to run stuff like your name node, resource manager, your Embari server, Hive server 2, store your metadata, all those sorts of things. And then worker nodes are the basic slaves of any Hadoop cluster, running node manager, data node, all that kind of stuff, the ones that are actually executing all the tasks. This is a pretty standard setup to see in most any cluster. We just really kind of refined it down to make it very simple for installing in the cloud. As I already said, there's actually two products in here that you use when you build this. There's the Cloud Controller Service, which runs on a technology called CloudBreak, and the Hortonworks Data Cloud, which is HTTP, right? Based off of HTTP. It is not exactly HTTP, to be clear, because there's not everything in a full HTTP installation is there, but it is based on HTTP, uses the same technology. An important thing to see here is, for simplicity, we've controlled some variables like what operating system it runs on, the JDK it uses, what database it stores the metadata in. All those sorts of things are pre-configured, so you don't have to spend time worrying about that and picking all that. That's done for you. Makes it very easy to set this up quickly, tear it down quickly. So what does it look like to actually do this? And again, I'll walk through this, but just to give you an overview first. First you have to subscribe to the products, and I'll show you where you can do that. You need to launch your cloud controller. This is kind of your master that controls all the different clusters. This is going to run on one machine somewhere in AWS. Then you can create one or more clusters and run those. And once those are up and running, you can resize them up or down as necessary. You can clone them if you have a cluster that is what you like, you want another one of it. You can make templates of your clusters, so it's very easy to create the same kind of cluster over and over. And then finally, when you're done, you can terminate that cluster or a set of clusters. So I've stressed that we're trying to make this pretty easy, but we want a little bit of configurability, and so we created both a basic and advanced option here. The basic option is really for getting started, for playing with it and seeing what you can do and how you can use it, whereas the advanced is if you're going to do more serious work over time, you're probably going to want this. In the basic, the two big really variables there are which VPC it's in and where your metadata is stored. So in the basic option, it creates a new VPC, virtual private cloud, and a new subnet and works inside there. In the advanced option, you can connect to an existing one. So if you have one already, you can connect those together. On the metadata side, in the basic option, we actually set up a Postgres SQL server to store the Hive metadata in for your tables. That means that when that cluster goes away, your metadata goes away. It's kind of you lose it all sort of thing, which is why you can see why this might not be a great option for more production workloads. In the advanced option, you can actually use Amazon RDS to store your metadata, which means that from day to day, as you set up different clusters, that metadata is still there. In fact, you could choose to share that metadata across clusters if you needed to. That obviously also brings additional costs because you're now using another Amazon product, so that's also something to factor into your thinking there. Finally, a note, which just because you'll see this and you don't want it to shock you, the first time you log into this, your browser is going to say, wait, this isn't secure because we actually generate our own SSL certificate when we do this. And so your browser is not going to be able to authenticate it, so you'll need to tell your browser, yes, this is really okay. This is just as a warning, so you know when you log in. Okay, so let's actually look at some of these pages now instead of just talking about slides here. Okay, so So first of all, where do you get to this? You find it on Amazon Marketplace, as I said, and I knew that Teradata ad would come up right when I pulled that page up. That's brilliant. So if you go to Amazon, or the AWS Marketplace, search on Hortonworks, you'll see both those products come up, both the cloud the controller service and HTTP services. So again, you need to pick both of these and subscribe to both of them to make this work. When you do that, you will see something that looks like this. This is the page for the controller service. And you would go through here. This will tell you everything about it. You can look at prices, how much they're going to charge. This price is on top of course, your Amazon infrastructure cost, which is dependent on where you run in Amazon and all kinds of stuff. And then when you click through to continue here, I think it will let you, let's see what happens. Whoops, it will tell you you haven't logged in. Well, I'm not going to log in on a live computer on a demo. So anyway, if you click through there, it will give you an option to launch the cluster. So let me see. Actually, that one, that's not the one I wanted. Oops. Okay, so when you do launch your, it does have an if user equals Alan. When you launch your cloud controller service, this is what you'll end up with, is something that looks like this. And we pre-created a cluster here, just because it takes 15, 20 minutes to actually get this up and running. You can then, so you see in here, there's an active one. If we, actually, let's just walk through real quick what it would look like to create one. So if you hit that create cluster, I'm not actually going to run one all the way, but I'll at least give you an idea. So you create like Alan live demo. You name your cluster, pick your HTTP version, pick which one of the 4 cluster types you want. So let's look at like the LLAP one. You can then pick for your master node, what instance type do you want? For your worker nodes, what instance types do you want? You can even add some options to those as far as attached storage and that sort of stuff. You need to give your SSH key pair. So this is actually something I skipped over in setting up the controller service. You will need to have an SSH key pair registered here with Amazon that you can use to communicate with us. That's how we're going to know, we can authenticate you going back and forth. You give that key pair here. This is an opportunity to lock down what addresses can access this and from what ports. And then you set up a username and password that can get into this. And then when you hit launch, you would end up in, where was it? Whoops, not there. Wrong lever. You would end up here. Showing, there'd be one in progress, and it would show it starting to get going. So let's look at this cluster that we have up and running that's going. So you see, you click on that. We're still in the controller at this point, but it shows you what, this is a 2-node cluster. We went for something really simple. The history of setting the cluster up, and then you see there's connections to Ambari, to Zeppelin, to other things. So you can go here and say, let's go look at our Ambari web view of this. And let's hope that Robert uses the same password for his Ambari that I do. Yeah. So you can get the dashboard for your cluster right here. You can see all your services running, see how your name node's doing, how everything's shaping up there. Take things up and down, whatever. And then you can do the same thing. You can start up a Zeppelin instance here. And from there, get started on creating, let's see, log in here. running queries and that sort of thing in Zeppelin, right? And this is already attached to that cluster. Looks like Robert's already got a whole set of preset notebooks there that you could use. Those, just to be clear, don't come with the product. But you can build your notebooks here, work with that against your data. So that's a quick overview of what's in here, kind of what you can do, how easy it is to do all that. Oops, not what I wanted. If you go back here, so when you're done, no, I didn't want to be over here. When you're done with this, and I'm not going to do this right now, but all you do is hit terminate here. That turns off the cluster. You're done. It tears it down. As I said before, you could clone this. If you want another one like this, you could resize it. So if you decide, oh, this is great, but I don't have enough horsepower here because I only put in 2 nodes, I need 5 more, you can hit resize, go add your nodes, and you're ready to go. So that's a quick overview of what's in there, kind of how easy it is to work with this. I will hand it now over to Gopal, but first, before I do any, sorry, whoever's next, Mingling, I guess, is next, sorry. Any questions before we switch over? Yeah.
Quick question about the cloud break. The impression is that the container management architecture, especially I'm wondering as a cloud break is working, how that's working with the container management. Is it using Marathon or Mesos based feeling, right? Do you mind repeating the question?
Okay, so the question is, how is CloudBreak working with the container management?
Yeah. Is it Mesos-based or using Kubernetes?
Is it Mesos-based or Kubernetes-based? I actually don't know the answer to that question. Do you know the answer to that?
I didn't actually quite understand what you mean by we don't need either. We have AWS that actually handles the.
So it just interacts directly with AWS to manage the containers.
Yeah, and the containers on per node is actually controlled directly by CloudBreak.
Oh, okay. First, quick question is how can deploy that? Is when I go to your preview, I saw that your looks like your formation script to deploy an application in AWS.
The CloudBreak formation script would.
Formation script.
Yeah.
Yeah. Compared to the formation script, why you select the formation script instead of Terraform?
Instead of.
Terraform.
I actually don't know. I use this stuff.
Yeah, I was going to say, the people who made that choice are not here tonight, so I don't think we have the answer, sorry. Sure. Other questions? Yeah?
So what's the advantage compared to EMR?
So why would you do this versus EMR? So I think we feel like,
Zeppelin, because there is no Zeppelin.
sure, so you get Zeppelin, you get an integrated cluster. We want to build on this with a lot more metadata services and security and things to make it very rich. We also believe that the Hive LLAP work is revolutionary as far as what it enables you to do for analytics against a Hadoop cluster. So that's where we feel like the advantage is there versus EMR.
Do you have any comparison benchmarks to Spark SQL as we're talking about Hive or that became better right now, not better since 1.6 in finally stable.
Sure. So I think the difference, well, I don't have numbers of one versus the other, and both are supported. If you want to use Spark in there, in this, it's fine.
Always ultra slow.
Right. It's no longer ultra slow.
So that's the reason why I'm going. So you're saying that that's the advantage. So I was wondering what are the at least relative numbers. I'm not 50%.
What's
I
that?
think a security model would be the biggest thing.
Yeah. Well, security and shared, the fact that you've got one cache shared by all the users, right? If you have a multi-user cluster, LLAP is going to be a much better model for you in terms of security and sharing the caches. I think Spark is really focused at and very good at. You've got one guy who's going to bang on a data set and put it down and go away. It's no question it's great for that. It's easy to use, very fast. Hive is focused more on I've got a whole group that wants to use this, and I need to figure out how to let them share it, resource manage it, and all that stuff. Right? Does that make sense? Okay. Others? Nope? All right, go for it. You want...
Better? Okay, so today I'm talking about the S3 guard. It's about the consistency model when you use S3 and running the applications in the cloud. So I'm Minglang Liu, and Steve is also this works mentor and co-author. So Steve is the author of Swift connector. He is also the mentor of Hadoop FS spec, and he's also working actively on Spark. And this work is also benefits a lot from other folks' careers, research, and mostly importantly, the Apache community. So the first thing when we run the application in the cloud is to use a file system like Spike, because this is the general stage usage pattern. The left finger is about the pure HDFS set, and the cloud storage is just the archive store. And then when you run the applications in the cloud, actually you want to change to the final pattern, which uses the object store like S3 as the input and output. But the HDFS is just like a caching layer. That is because when you run the application in the cloud, you don't want to have your HDFS cluster running always if you turn off your clusters, and you don't have to pay for the cost. And if you turn off the cluster, most of the data, the ephemeral storages devices will be gone. So as your data. So you don't want to run that as the general pattern. So when you use the S3 object stores and HDFS, the file system API is the one interface that fits all patterns. So everything uses the Hadoop APIs to talk to the HDFS, the Hadoop compatible file systems like WASP, and most importantly, the object stores. So under the FS API is the object stores. So when we are talking about the file system, it's about the directories and the files to mapping to the data locations. So the left finger is very simple, tree-like structure. It has two subdirectories under the work directory. And if you do a rename, actually it will move the metadata to another tree subtree, but the data is not touched. So if you are familiar with HDFS, so the data nodes will not move blocks because of this. It's a pure metadata operations. S3A is the object store that it pretends to be a file system, but it was designed for scalability for low cost and geographic distribution and high availability. It's not a file system, though it pretends to be a one. And when people write new apps for the cloud storage, they dedicatedly deal with the semantics and limitations of the S3 like object stores. But the Hadoop applications, we don't want to change our application, when we migrate our existing applications to the cloud. So we use S3A. But S3A partially adheres to the file system specification. I will show some examples later. So here is the object store. It basically is a hash map between the name and the blob files. There's no structure here, actually, though we, by some contracts and it has the slash and the tree-like structure, but it's purely flat when you have a bucket. And when we use the object store as the underlying storage, it has some problem. What is there are actually 3 of them. The first one is about the performance. Because the S3 is an remote object store, it's not like the traditional Hadoop applications where the data node, generally is the same cluster. So you can run your applications very fast using the Ethernet. And the cloud storage is also not designed for file-like access patterns. For example, it does not support very comprehensive APIs like delete recursively and rename. So for delete recursively, it can be implemented. Actually, the S3A file system does this. It lists all the files in that path and then deletes in patch parallelly. So it's not atomic. And for the rename, actually it will copy the old data to a new data and then delete the old one. So this is the limitations of the object store. And when we write a mapper as a S3A file system client, so we cannot address these problems from the server side. So we have to do this in the client side. The client has to copy the old data and delete the old data after that. The biggest challenge actually is the eventual consistency. So the S3 supports, eventually a consistent model. So if you create a new data, you will you can use the get or head HTTP request to get the data immediately. But if you update an existing one, you may still see the stale data content. And if you delete an object, you may see the old object is still there. It's not deleted. And if you list, a bucket, firstly, it will take time, to list the newly created object. This is different from the get, because get is a single request for one single item. And it will in change the metadata change about the existing objects and deleted ones. So today we are talking about the eventual consistency and try to address that problem. And the current phase is the listing consistency is already finished, and we are working on the delete, and update will finally be addressed in weeks, not months. Hopefully, we can ship this one with Hadoop 3. So this is a very simple example about rename. If we rename, so it will copy the old data to new one and then delete. So it's like a series of operations from the client side. Given the eventual consistency problem, from the file system's point of view, we see some unexpected behaviors. When we list a directory, so the newly created files may not yet be visible. because the objects is not visible. And after we update an object, we can still, if we open and reading the object, we may still see the previous data content. And after deleting an object, a file or directory, you may still see it open is still successful and the data is still there. But eventually it will be gone. So yeah, this is about the delete. So here's one example about seeing deleted data. So here we had some one per object, so one file. Sorry. So it's there, and then we issue a delete request. So it deletes, but it goes to the second server, not the first one. So if we it will go to the first server. Still, we can see the object is there. This is because of the intrinsic feature of the S3, because of the high scalability and availability. So S3 is eventually consistent store. That this behavior is very easy to reproduce, actually. So to address this, we proposed the S3 guard. It's a fast and consistent S3 metadata store. But if you run the, on EMR, actually you have existing implementations of the EMR FS. It's a very similar idea, but it's closed sourced, and you cannot use it out of EMR system. So the S3 guard is fast and consistent metadata. This one was inspired by another open source project, S3 Mapper, from Netflix. And the basic idea is that it's very similar to S3 map. So we use a secondary index store as for the metadata, and for the real data, we still goes to the S3. So we choose DynamoDB as the consistent metadata store. We know that DynamoDB provides also two consistent models. The first is for each request. Almost each request, you can specify the eventually consistent or strongly consistent. So to address this, when we use DynamoDB, we have to use the strongly consistent approach. And basically, for two kinds of operations, the first is mutating operations, the write operations. So we will update the S3 and DynamoDB both. For read operations, we will retain the final results still to the columns still sourced from S3, but we will first check the results against the secondary index, say DynamoDB. And if there's any disagreement, we see inconsistent behavior happened. So we S3A, that file system will wait and checks until they agree. And this is our goal. The first is to provide a consistent list and get status operations if you use the S3 guard as the strongly consistent model. For both post and delete, the list status and get file status will retain consistent data because we checked and wait. The second is we also provide some tools to manage the associated metadata and the caching policies, strategies. So for the inconsistent behavior, we will also provide some configurable error handling tools. And for the performance improvements, that will be also one of the targets because we have the metadata in a fast and very small metadata store like DynamoDB. It will be very fast to get the to list a directory. The performance gains is also one of our goals. So here's the basic structure of our design. So still, we have the 4 operations. We had an existing one file and delete it and hide it again. So it will go to the DynamoDB first for the read operations, and for the delete, it will also update both the DynamoDB and the S3. For the head, it's also a read operation, and for the put, yeah, it will also update the both, because the delete and put are mutating operations, and head and get are read operations. So this is the very simple idea, actually. So yeah, I can show a very small demo. After that, I will show some current Jira status. So for the demo, let me. Okay, so it's very small. I will. Can change the font size. Okay. So I show one very simple example. Here's because the inconsistent behavior. For the program, we use a very simple simulator. It will delay the. It extends the existing Amazon S3 client, but it will delay the results for a fixed time interval. So if you create a new file and then running list, so you will see you will not see the file immediately. After a fixed time of interval, you will see that. So this is the basic idea. Yeah, I tried. Okay. Okay, yeah, this one is the basic. Here's a very. This path is returned by the inconsistent simulator with a very fixed time. And here we run the program. So we run it 3 times so to see if it will fail. So right now we are not using any metadata store protection. Here we comment it out. So we expect that this test will fail in 3 times. But if we, okay, yeah, good. So here we see that the bracket. Test bracket is not exist. I have to create the brackets. But S3 test, yes. So here we create a new bracket. And we run the program again. Okay, so it fails with the exception message that all paths should be included, but it's not. So here we enable the DynamoDB metadata store. Here, sorry. Okay, so we enable this one using this convey key and run the program again. By the way, we can actually have a look at the DynamoDB table. Here, there should be some, okay. This is the S3 guard test. And when we put the item, there's, okay, so it's empty. And we run this one with DynamoDB. If we refresh here, if we are lucky, we will see the item is here. Sorry, the test runs cleans the data immediately. I can show another demo that will keep the data. We can have a look at the other test. here. This is the schema of the DynamoDB table. This is the hash key parent, and this is the child, is the range key. So this is the parent for a path, and the child is the file name or the directory name. And it also has the other metadata information like block size, file length, and modification time. So here we run it 3 times. It succeeded. Yeah, succeeded. Okay, so this is the first demo. I like to see, because we are not using the real S3, we use hacked S3 client. It will delete the retain objects more obviously than the real S3. So for the second demo I can show is that because it's this program also creates some objects in the S3 and try to rename it. For that rename, it will call the list status. Get file status API. So that API will bring some inconsistent behavior, and we will see some file not found exception here. This one, because it's very hard to reproduce. I'm using a very high network. Sorry about that. And but if we enable the DynamoDB, we will not see this problem. So this is the configuration file, and we run this program again. So the current screenshot, if you can see it, is the file not found exception, because of the inconsistent behavior. And so this command uses the DynamoDB. Here we can see this is the S3 guard, test 3. We have looked at this table. There will be more items. 100, okay. Sorry, I'm not enabling it. That's interesting. Let's generate a brand new one. We call it test 4. So we create a new bucket here. Create a new bucket. Test 4. This is a new bucket, and in the DynamoDB table, there's no table created for that one. And then we generate files using this one, and it will create the DynamoDB table for you. So if you run the program, but I don't know why it's absolute. Sorry about that. And we will use the same region of the DynamoDB as the S3 because it will get more throughput. And okay, so we generate new data and then we run the program again. This is the test, so we have to change it to 4. Here, if we look at the content, hopefully we will see the sorry, don't see the table. That's okay. Yeah, the table is here. So this one does not exist before, and after we enable the DynamoDB metadata store for the S3 guard feature, it also creates many items here. So for test, and this is all the items. And if we run this, hopefully it will. It will succeed for sure because it has the strongly consistent model. But if we run without this one, we will see the test failure occasionally. So that's why I did not show this one. So that is about the talk. Yeah, so lastly is about the Jira that I'm talking about. So it's sorry, that's the Jira. Okay, yeah, this is the Jira. If you like to know more and the current status, you can watch this one. And yeah, if you have questions, I'm here to answer this one or after that. Okay, yeah.
So what is the motivation behind trying to use S3?
So are you asking about why we are using the DynamoDB? Or
And now S3 storage for it's already well known, right? S3 has its use.
oh yes, yeah, that is a good question. I should have covered this one in the motivation page. I should stress this further.
Could you repeat the question for the folks live streaming?
Yeah. Okay. So the question is about why we should use the S3 object store if we can use the HDFS if we run Hadoop applications in the cloud, right? Okay. So generally, if the user migrates their Hadoop applications right now, they may set up the Hadoop cluster, HDFS cluster in the cloud. But if you finish your job running in the cloud, users may want to shut down the cluster in the cloud, and next time when you have to run the applications, you start a brand new cluster. At that time, the HDFS, if you shut down the cluster, HDFS service is not available. You cannot read or write until next time, and you cannot share your data with other applications because you shut down your cluster, right? And also, most of the
So, I mean, just to clarify.
yeah.
So you were saying that when you run Hadoop with HDFS in AWS, so HDFS is using local storage at the point in time in the compute runs, or whatever those.
You mean the ephemeral stores? Yes, yeah. Actually, you can also use the EBS, but if you shut down the instances, you still have to launch instances to mount that persistent stores about the EBS.
So that's the motivation, is because EBS is expensive.
Yeah, yes. Yes, basically if you have to keep your cluster running always and always keep the, pay for the storage you are not using, so you perhaps don't want to migrate to, cloud. And this is a very important pattern that we are addressing. Yeah. Okay. No more questions? You can get back to me after that. Okay, thank you. Sorry? Yeah.
Cloud storage as the primary data.
The lake, it's basically, the storage, the huge storage of, your data after you run the application. So it's the final output. You can think about that, like the final output. But for the intermediate data, the temporary data, you can use the HDFS as the, temporary data store, and you are free to shut down your instances, and the data will still have 3 copies, right? And you can employ the spot instances, so which you save cost further. You can, if the spot instances are closed, you still have other copies of the data nodes. So it's suitable for the temporary data, but it's not for the final output of your application, because without that, you have to rerun your application to get the final output. Yeah.
So is there any performance impact?
Actually, if you use the object store like S3, you will see performance degradation, because I talked about, because the first thing is S3 is not local; it's a remote. Though you have, yeah, we will see performance degradation, but for many applications that it's not for the final output and the beginning, the starting input is acceptable. But for the intermediate data, we can use HDFS as the third picture shows. We can still use the HDFS as the caching layer for intermediate data, so it's still local on your distances. Yes. Yes, please.
Can you use Spark to replace Hadoop for your system?
Yeah, sure. Because we are talking about the file system here. Yeah, from this page, actually what we are doing is like an enhancement of the file system, S3 file system API. So the applications can use this file system transparently. You don't have to change anything, just to, like what I did in the demo, enable the config key. That's it, yeah. Okay, sure. Okay, thank you.
Hey, is it on? Yeah. So my name is Gopal. I work on LLAP. I don't know if anybody's heard of LLAP here, but LLAP is the data cache layer for Hive, and lets us run sub-second queries on file systems that are far away in the cloud. But what LLAP does for read, to be able to read faster from the cloud, we want to be able to write data faster to the cloud. So this is like a talk on some work that we're doing to make writes to the cloud faster. And to sort of follow the same theme as the previous one, cloud file systems are not really file systems. They look like file systems. You use them like file systems, but they don't actually behave like file systems at the lower level. And these are sort of like the 4 ways they're like very different from file systems. One, there are paths. Every file has a path, but there is no such thing as directories. There tends to be this, when you look at a file system, you think of it as being organized as a tree, where you traverse each level of the tree, and you can look at everything at that level at one point. Whereas in like a cloud storage system, there is a path, and if you know the path, you can go find it, or you can get a listing of the path. But to think of them as directories is probably a mistake. Second, usually for file system implementations, there's a concept of the user who's accessing data, and that user is actually offered by the system in some way beneath the system. But for cloud systems, there tends to be an access key. Anybody who has the access key, no matter what user they're running as, has access to the data. And finally, there are no such concepts as permissions in cloud storage. And everybody knows there are actually permissions. There are like files you can read and files you can't. But they tend to be path patterns, saying that anything below this path cannot be read by somebody. Whereas in regular file systems, the permission flag is actually set on the file. Like for every file for a directory, you go and attach a permission. Which basically means if you're traversing and finding a particular file in a file system, you have to go through every part of that file system path, find out whether you have permission to access every step of the way before you get to the last end where the file is and read it. That is completely bogus with the cloud storage systems. There is an ACL rule saying that I can access this file or not, but that doesn't mean that I have to check it every point. And finally, there is consistency, and there are consistency rules followed differently by different file systems. They're not the same. And as the S3A guard said, we can sort of normalize some of the consistency problems, but still it's better to avoid some of the common pitfalls you can have. Now, once you decide to actually store data in these systems, you start to learn some very leaky abstractions that start to pop up. Because even though you are treating it as an abstract file system, same as HDFS, you have to actually take a little more care to use these than HDFS. Now, the easiest way to think of this particular storage system is to think of it as like a store which contains a sorted hash table. And there's a good reason why I mentioned sorted hash table, is because when you start to look for a subdirectory for a given directory, in quotes, what it actually does is it does /* does not have a slash, does not have a slash in it from that point. It's actually looking for everything underneath that which doesn't have a further slash. It's not going to that point it's not going to the node that you asked for and give me a listing from that node. It's searching a space which contains many, many paths. And because of this, the parent path directory doesn't even have to exist for a final path to exist. So if you have, like, let's say /tmp x/y, In a regular file system, you're guaranteed that if you try to access /10/x, it will exist. A cloud store doesn't really guarantee that. And if you do create one of them, it's actually wasted objects in the system, which only you are expecting, but the internal bookkeeping system has to keep it separately in a different storage. And because of the search pattern thing, when you traverse a file system, you get to find out that traversing a single level of a directory, as in give me all files under this directory, is more complex than find me everything under this directory. Because find me everything under this directory is /star and just give me everything. Because every other path is has the same prefix, right? It's just a simple prefix search. Whereas finding just the single level actually finds out, okay, so is there something x/y? Does y have a slash in it? Is there other things underneath it? It has to do a little bit more work to find out just that level. So which means that a deep directory structure is not more expensive to traverse than a single level directory structure. And this gets a little more complicated when you start moving data into these systems, because of the listings and prefix searches, it makes more sense to store data in some sort of sorted order, like that is a metadata. And we sort of found this when we tried copying data from HDFS onto S3. We had a list of files, and when we took the listing, it would end up in sorted order because that's sort of how HDFS would store it. And then we tried to insert it. Inserting files in sorted order takes more time than inserting them in random order, right? Because if you think about it, if you're putting a bunch of paths into it, or if you're putting a sorted list into a binary tree, you notice that the binary tree has to do a lot of balancing to remain balanced all the time. Whereas if you just inserted them in random order, it'll sort of fall in order, but it will never be like left leaning and have to balance to get everything right. So, in some sense, files that are next to each other in a directory can sometimes be slower to modify than files which are like randomly spread across when you modify things. So, the next part, user permissions ACLs. This is another one of those problems that because we treat it as a regular file system, we have to actually check for like, is this user have permission to every directory above it before going deeper? And even though there are mechanisms to maintain user identity separate from these keys, it's sort of mixed to the point where like, if you have a key, you pretty much have access to everything in the bucket unless you get an error. Explicitly having to check permission whether you have access to this file is entirely pointless. You can just go look for the path you want. If it comes back to you, you have access, right? And because none of these permissions are like set in the per file or anything like that, you don't actually have to worry about in a bucket whether different users are going to access it. Because if a user has a key that gives them access, the file system implementation can completely ignore everything and just delegate all permissions to the cloud storage. And finally, consistency. And consistency is probably like the most argued upon thing, because the definition of consistency for people are different. Because eventual consistency, as people argue, is not consistency at all. It basically means that like you hold your breath for a bit and then try again, maybe it works. And because of eventual consistency, a lot of assumptions systems make about saying, if I rename files, nobody else who's doing a rename right now to the same file name will succeed. It's not true anymore, right? You get to find out that one of them won the battle later. And at which point you have no idea who is supposed to do any reruns. It's like too late for reruns. The create for files, saying the first one to actually open and hold a file handle might have an exclusive lock in a file. Probably not true. You might actually overwrite a file with a file name with a similar name, well, the same name. And you might be reading it from this machine and another machine, and you might have like a 3 replica scenario on the other side where you get like 2 replicas would have the correct value. It's a raft kind of consistency system. And the 3rd replica might have a stale value. A system like S3 does not guarantee any of these things would really work. So the ideal scenario is that if you have a file name, you never want to use it again. That you create a file once, you delete a file once, you never try to modify that file ever. And it's really, really difficult in Hive today. Because what Hive does is Hive has a particular path into a directory into which it writes data. and it does something kind of stupid, because what it does is it tries to take the task name of the guy writing file and use that task name as the destination target file. So which means that if you do an insert, then you do another insert override, there's a good possibility completely different data files from the same data being reinserted will end up in different files. And if you have any problems like this, by the time you actually call up somebody or try to debug this, the problem disappears. Because that's what eventual consistency does. Because it never gives you enough time to debug, and you always have problems. So, this particular branch of Hive tables tries to use a few of these things, few of the things I discussed earlier to its advantage, and tries to avoid some of the problems that you commonly encounter. So, we call them micromanaged tables because they're managed tables which are managed a little bit more than before. And it entirely tries to avoid rename as an operation. Like, when we started, we were like, okay, we don't have any renames, because the way Hadoop usually does the file commit is to rename, and the first one to rename sort of wins the commit. And that doesn't work at all. So there are no renames in the system, and if you run two instances at the same time, they don't have collisions, right? And the way we do this particular operation is by creating like a write ID every time you try to write data, and create a separate write ID directory for each writer that is currently trying to write data. And like I mentioned earlier, creating more directories is not more expensive in a cloud file system, because it doesn't actually add any more overhead if you can just say recurse scan, right? So this particular table structure gives us a little more comfort in knowing that if a file exists, it was only created once. It was never modified from that point onwards. And you can separate an insert that was done yesterday from an insert that is done today simply by looking at where it was written. And because this is not sufficient for every problem that we have, we actually also added like a little bit of protection on how this data gets read, saying that if you're inserting, say, 10 partitions, and you have a failure after inserting the 9th partition, the previous 9 partitions should not be considered as inserted, because when you try to insert it again, you don't want to end up with 9 plus 10 and 19 inserts of the data. So cleaning up of data that got inserted partially and the system failed for some reason is something to be avoided. And the reason I bring that up is because this is not really such a big problem when you come to like a HDFS, like a in-house cluster, because if it goes wrong, somebody's immediately going to go fix it right away. Whereas for a system like S3, you won't even know that it failed. That you will just get an error, you try again, it would succeed, but you wouldn't know whether the previous insert was completely deleted or not. Somebody would have to figure out which file in the previous insert you had to find and delete. And that's kind of impossible. So we sort of have like a write all your data, clean up all the junk data that showed up, like failed returns and everything. And then finally, make a commit into a transaction database that says that this data is actually valid. So, whereas previously what used to happen is you write all data into a temporary location, then rename it into the correct location, and hope that the system stays up during the rename and nothing fails. If you kill something during the rename, you would end up with like junk data in your storage. And a little bit of this thing gets more complicated when people try to do bucket replication. They'll have a Virginia bucket, they'll have an Oregon bucket, and they'll try to replicate. And half of the data will show up in a listing, the other half won't. So we created this new table type called Micromanaged Hive tables, which require 2 parameters to be set, the transactional true and the insert only. And the reason to say insert only is because if you don't do insert only, it only supports one format today, ORC. If you do insert only, any format can be written in this structure. And it sort of ends up looking like this. I don't know if everybody can read it, but I've highlighted the part that marks the transaction numbering or the insert ID. And it sort of works by creating 3 extra directories. You can see here. Maybe we can skip some of those directories at some point so that we just create the path that we intend to write to, not the directories. And the insert code path sort of works like every writer that shows up takes a number and then uses that number to write, and erases that number from the list when the write is complete. So that the list of numbers that are currently open is the only list that you need to maintain. You don't need to maintain a list of everything that has been committed. This is very similar to the Hive asset implementation that we have. It's pretty much like a 1:1 copy of the idea there. So the number of inserts you do has no impact on the metadata that you need to hold. The metadata is only the number of inserts that are currently active or aborted. And that list is actually sent as part of the query, which sort of gives you a snapshot of what is currently inserted, and it gives you a list of inserts to ignore, or directories to ignore. And that's plugged into the path listing, which is outside of the input format. So the path gets to see something slash mm0, mm1, mm2, mm3, and it can deal with those directories anywhere they want. So this gives us a improvement in the way we insert data into the system, particularly because we don't have to wait for renames. We only have to wait for deletes. Deletes are not particularly fast, but they don't really require any rebalancing of the metadata in the backends, because it just mark them as dead and move on. So it gives us right now like a 20% improvement in the amount of time it takes to load data into the system. The work is sort of continuing on this particular branch. We are planning to take advantage of a little bit of the faster recursive listings, so that you don't actually have to have a directory named mm0. You can just pretend to have a directory named mm0 if the path is an mm0. And little bit of question of if this number is actually always going up, can we use it for like incrementally figuring out what got inserted from A to B at some point for like other information? Because we don't support any deletes in this particular operation, you don't have to worry about any previous data changing. Only that if yesterday got some extra data added to it, can we figure out yesterday got some data added to it quickly without keeping track of all the files with a single number stored up for yesterday. So, questions? Yeah.
I have two questions, but I'm not sure the question is right. See, when you come for the consistency, right, is there a possibility, like Cassandra, right, quorum concept is there, right?
Yeah.
Is there something possible for this use case? That's first question. Second question is like, this is a very basic question. How does EMR handle these kind of issues? EMR should be hitting S3 issues, right?
I can sort of answer the first question. We're not doing.
Summarize it, please, for the
Yeah.
video.
So the question is like, how does like something like Cassandra consistency quorum thing relate to this? The consistency problem is actually on the other side of the cloud file system. It's not on the side that is actually writing data to it. That side doesn't actually handle it at all today, which is why we have like S3A guard. But even in that case, we never want to reuse a path, because if you don't use the same path, you will never get any consistency issues. But there are two consistency issues we worry about. I don't know if this is visible in this particular thing. One is like a list after create checkpoint, and the other is a list after delete checkpoint. So if you create a file in machine 1 and do a list of that path in machine 2, do you get all the files created? Maybe, maybe not. You delete a file, you take a listing, do you see the deleted files there? Maybe, maybe not. Right? So this doesn't fix all the consistency problem. This just fixes, is this the right version of a file or not? You'll find a file that is supposed to be there, or you'll find a file that is not supposed to be there, which is easier to debug than a file that for a little while has the old data. So it doesn't solve the consistency problem. Consistency problem is still S3A guard or something else that gives list after delete and list after create across multiple sources. And the second question was actually more, how does EMR handle it? I have no idea.
No, I was just curious. EMR also works in S3.
Yes, so EMR also works on S3, but I have no idea how they handle the consistency of data that goes into the system. It's not a question of what happens when the system fails. It's also a question of what happens when you're inserting data, you're halfway through and you hit Control-C from the user side. What is the expected behavior? Is it expected to clean up everything that it inserted? Where does it keep track of that information? I don't know. But if you want to do this, you have to have some sort of mechanism to say, separation between files that were inserted by this particular query and files that were inserted by another query. And that will reflect in the way you store the files. Or you store them somewhere else where you can't see them. But I don't know. I hope they do that, because otherwise people would end up with 19 inserts when they wanted to insert 10. Yep.
A couple of questions here. So you're advertising that you're supporting ACID transactions in
No.
At least robustness ACID. I've seen that on the website. So
No, that's different from this particular model, because that's actually for ORC data only,
that's only for ORC.
where we can do insert update delete as well.
Okay, but how you do the standard, let's say record logs? How do
Yeah.
you deal with that?
Record logs, we
Yes.
have partition logs. So if you're updating a single partition, only one writer is actually allowed in.
So it's per partition.
Yes.
So you mean per directory?
Effectively per directory, yes.
Per directory.
Yes.
But only for updates and deletes.
Yeah.
Inserts and reads can always proceed, even in the face of an update or
So multiple inserts are allowed in.
Yeah, makes sense, because that's usually at the record level, right? So
Yes.
insert doesn't matter, right?
Yeah.
So it's only for update and delete that you have
Yeah.
had the issues, right?
Yeah.
Okay.
So this one doesn't do updates or deletes easily.
Yeah.
So it doesn't
Yes,
have that
100%. How do you do it here? Okay, the other question is that you kind of were not focused on this, but I kind of looked at the LLAP, and you're doing a lot of things in memory now, it seems in the LLAP.
Yes.
So kind of like the same thing that Impala does, and I've seen some benchmarks that you have there.
Yeah, it's not the same, but slightly different.
Yeah, at least I mean the memory concept.
Yeah, as for a user, you wouldn't probably compare. You would probably compare that, but the way they
Yeah,
work.
I saw the benchmark on the website, so that's the reason why I'm going with
Yeah.
this. And so how are you doing actually? For instance, Impala has a lot of issues when you run out of memory.
Yeah.
So how you solve this problem?
Okay, so the question is like,
Because in Impala you add more memory. That's the solution.
yeah, so the question is actually about LLAP and how it handles memory. So LLAP actually does very similar things to what a constrained container model in MR or Taze would do. Whenever it runs out of memory, it spills. And whenever it can't spill, it tries to distribute. Right? So it tries to divide her into as many fragments as possible. And you can run 10,000 fragments or 10 containers. They will just run one after the other. So that's how it handles it. The part that is different about LLAP is LLAP has a cache, in-memory cache. And LLAP is like an on-demand cache, which means that it has a cache that is populated by you using it, rather than you deciding to cache stuff. Because every time we give the scaling bit to the user is like, yesterday I wanted to go left, I can't see today, I will go left. Right? So we sort of tend to have these Black Friday events when a user decides to cache everything and nothing fits anymore, and everything crashes. That's great when you're trying to do a benchmark or try to like sort of give a demo. You cache everything and run everything is fast. Whereas what LLAP tries to do is LLAP is built for abuse. It's built like a truck, not like an F1 car. Right? It's built like so you can just load stuff in the back, run it. And what LLAP, the cache is meant to do, is it's meant to be optimized for two different cases. One we call dimension hopping, and the other is actually drill down. So dimension hopping is when you say you want call drop rates for zip code number 94140, right? And you don't know whether what the user is going to do next. So while doing that scan, LLAP collects an index of which all files have which all zip codes. Like it doesn't collect exactly the full list, but like ranges and a Bloom filter. The next time it gets a different zip code, it goes through this index rather than the full cache, finds out which file it needs to read, and then reads that file from S3. Right? So it maintains like two different levels of caching, and it can drop parts of the cache sacrificially of sorts, so that you have, we sort of call it the last hour problem for BI systems. You load like terabytes and terabytes of data in a cluster, but the last 20 GB that came in this hour is what everybody wants. Right? So we try to replicate that kind of data in LLAP, so that we don't keep reading it from S3 all again and again and again. So sort of like a nearline cache.
Thanks for coming out. So we have, I think, our last meetup of the year is next week, December 13th. It's not going to be here. It's going to be near the 49ers Stadium. And that's going to be focused around Apache Spark for machine learning. So it's going to be a little bit of introduction, but it's also going to be leveraging this AWS infrastructure to run Spark. And then so that should be the last meetup of the year. And then after that, we're looking at doing some hands-on meetups, so they kind of get you actually hands-on with this for a particular tutorial. So that'll probably happen the beginning of next year. So thanks for coming out, and hope to see you next week to get a little deeper with Apache Spark and on AWS with this infrastructure. Thanks.